Okay, so the real beauty about standard deviations is it's going to help us figure out the likelihood of certain events. So we're going to get into this more when we talk about z-scores, but for now we're going to cover something called empirical rule and Chebyshev's theorem. I think they call it something else different in your book, but that's essentially what it is. So empirical rule, pretty straightforward. So it has to do with how many standard deviations a data point is from the center. So many histograms have a single mode near the center of the data and are approximately symmetric. Such histograms are often known as bell-shaped. So if we have a bell-shaped histogram, we can use means and standard deviations to help us figure out probabilities or likelihood of particular events. So when data has a bell-shaped histogram, it is often possible to use a standard deviation to provide an approximate description of the data known as the empirical rule. And what empirical rule says is that I expect about 68% of my data to be within one standard deviation of the mean. I expect about 75% to be within two standard deviations of the mean, and I expect almost all of my data to be within three standard deviations of the mean. So actually we have a number for this. Your book kind of ignores it, but usually we say it's 99.7. But it is to practically all your data should be in that range. So this is just a picture showing you. So remember, this is mean. This is the standard deviation. So let's say that my mean was 100 and my standard deviation is 15, which is true when we talk about IQ scores. So what this is telling me, empirical rule, is that if this is my mean, this would be 100. And this is my mean plus sigma. Well, this is my mean plus 15, so that is 115. This is my mean minus 15, so that'd be 85. So that tells me that within this range, that's 68% of my data. That means 68% of people, and if we're using IQ data, 60% of people have an IQ between 85 and 115. If we go out two standard deviations, that means I had to add 15 on 2 times. So that puts me at 130. If I go this way, I'm subtracting it 2 times, which leaves me at 70. So that means 95% of people are within 2 standard deviations, so 95% of people have an IQ between 70 and 130. And actually, like, this is the border, so 130 and more is what we consider gifted. Genius isn't quite there yet. Genius is 140, but 130 is like really gifted, and the 70 is when we start considering we have like a fairly significant mental impairment. So we actually use these standard deviations to kind of, depending on the scores, there's different ways that IQ is scored, but some of those scorings of IQ are based on standard deviations from the mean. 115 or more is when we start considering somebody to be intelligent or bright. 85 or less is where 85 is, I believe, is borderline impairment. So it's marking these boundaries for us that's based off standard deviations. So we use these standard deviations a lot, and especially like these empirical rules, we look at things as being 1, 2 standard deviations from the mean as kind of a way to, like, we put it in a category saying, you know, this is bright, this is gifted, this is genius, this is borderline impairment, this is a mental impairment, this is a significant mental impairment. And those are based on those, partly on those standard deviations. So the last bit of it, so if I went out one more standard deviation on both sides, 130 plus another 15 is 145. 70 minus another 15 is going to be 55. this range here, that's 99.7% or almost all IQ are between our Q scores. If we looked at all people, are going to be between 55 and 145. We don't usually find very many IQ scores out of that range. It is very rare. So we say almost all because we can't actually, for the most of the time, can't say all because there's always a chance that something's going to defy what we believe is true. There's always a chance we'll find somebody who has a really, really like, an IQ of 3. There's a possibility. I don't think we found that, but that's always something that we have to wonder about. Or there can always be somebody whose IQ is 300. Which is once again really, really, really unlikely. Probably never going to happen. But we always have to leave that kind of open. So that's why it's never all. It's almost all. Okay. So just for example here, so the following table represents projections for the percentage of the population 65 or over for each state in the District of Columbia. So this is population data. We got the percentage of people who are 65 or over. So we see like one state, about 14.1% of the population 65 or older. We have one where only 9% is. So there has to be a pretty good one here. I just saw it was pretty big. Maybe it's just a 16. So we see like different percentages. So if we put this data into our one var stats, our mean would be 13.249. And our standard deviation is 1.683. So if we want to use the empirical rule to describe the data, what we can do is this. I want a different color there. Tools aren't grabbing correctly. There we go. So we have a mean and a standard deviation. So if I took 13.249 and I add and subtract that one standard deviation of 1.683, calculator just closed on me, just a second. 13.149. If I subtract it, 1,693, that's going to give me at the minimum 11.566. And then if it's added, then we're going to get 14.932. So we expect that 68% of states are going to have between 11.56 and 14.93% of its population is going to be in that 65 or older range. So 68% of states have yeah, anyway, 65% are in there. I was trying to add more to it, but that's good. If we take that same mean, but this time we're going to add and subtract 2 of those standard deviations. So we're going to subtract it twice and then add it twice. So that means if I take this and I subtract 1.682 times, I'm going to have 9.883. And then if I add it, I'm going to have 16.615. So I am expecting in this case, because that's 2 standard deviations, I expect 95% of the states disappeared here, the states. States are going to have between 9.8 and 16.6% of its population is going to be 65 or older. So it gives me that range. We see there's a few that don't fit in this range still. We got that value right there. This one doesn't fit in that range. So if we go out one more standard deviation, in this case, I think it's going to include everything. This isn't always the case. If I go out 3 standard deviations, so 13.249 minus 3 times 1.682. That is going to give me 8.2 to I was surprised by that number to 18.298. So we expect, like I said, it's 99.7% or almost all, or it could be all states are going to be in this range. So we think that everybody, every state probably, and it seems to be true with this data. So for all states, we should find that we have between 8.2 and 18.3% of the population should be 65 or older. Okay. So this is pretty much what we use empirical rule for, is to kind of get these ranges where we can say approximately this many people are in this range. Usually what we're mostly interested is in this particular range here in the middle. A lot of times we're interested in that 95%. Because we're always going to have these like few little numbers that always are going to linger off the end. You always have liars you have to worry about. So what we're doing here is we're kind of, like I said, we tend to focus on that 95 because that is where a vast majority of our data is. Anything that's outside that range is usually considered pretty weird. Or not necessarily weird, but pretty unexpected. Not something that is normal. We tend to ignore things that are out in those regions. Okay, so same thing again. Getting that same data, approximately 68% of my values are in that range, approximately 95, and almost all of them are in that range. As you see, that was the minus a standard deviation, minus and add standard deviations, minus and add 3 standard deviations. So empirical rule can be used for samples as well as populations. When we work with samples, you're going to use the X bar instead of mu, and we're going to use the S instead of sigma. So this isn't just a population thing. We can use this on samples. So a large class of 200 students took an exam. The scores had sample mean of 55 and a sample standard deviation of 10. The histogram is approximately bell-shaped. So if we made a histogram, it should be approximately bell-shaped. Approximately how many students score between 45 and 85? So let me go through and explain that get rid of some of this solution here. So we need to look at those ranges again. So 68% are scoring between, and we have that mean of 65. So we take the 65 and then we subtract the standard deviation. So we subtract 10, which is going to be 55. And that mean plus the standard deviation. So that's 65 plus the 10. And that would be 75. So we want this range. So let's look at 95. We know that 95% of these students are going to be scoring between, so it's going to be my mean minus 2 standard deviations, or my mean plus 2 standard deviations. So this is going to be 65 minus 20, or 45, or 65 plus 20, which is 85. So we see that 95% of my students are actually scoring between a 45 and an 85. And we have 200 students. So we have 25 students and 95% score between 45 to an 85. So all we're going to do is take that 200 and we're going to multiply it by that 95%, but we write it as a decimal. So 200 times 0.95. So you always make your percents into decimals if you're going to do any calculation. And I get 190. So we know that 190 students scored between a 45 to an 85 on this particular exam. And that's pretty much what we expect, like most students should be in that range. If this was truly like everything was balanced. Okay, you might want to pause on this one. Take a moment, try on your own. But for a healthy human, a body temperature follows a normal distribution with a mean of 98.2. So this is actually was data that was gathered at one I can't remember, one college at one time or something like that. And a standard deviation is 0.26. Use the empirical rule to answer the following. In what range is 86, or sorry, try that again, 68% of all body temperatures? And then in a group of 60, approximately how many should have a temperature between 97.42 and 98.98? So we know that 68% is considered one standard deviation from the mean. I gotta move my slide back in place. So what we're gonna do is we're gonna take our data. So we have 98.2. I just have to remove one standard deviation. And then I just need to add one standard deviation. And that will give me the range where I expect 68% of all my body temperatures. So 98.2 minus 0.26 is going to give me 97.94. And then if I add it, I should end up with 98.46. So the range of 68% of my body temperatures is going to be between 94.94 degrees Fahrenheit to 98.46 degrees Fahrenheit. Okay. So in a group of 60 people, approximate how many are going to be in this temperature range? Well, we know it's not 68 because we already know what 68 is. Let's see what 95 would look like. So 95 would be 98.2 minus 2 times 0.26. So we just want to subtract 2 standard deviations. And that's going to give me 95.94. And then we're going to take my 98.2, but we're going to add 2.0.26. So we're just subtracting 2 standard deviations. Yeah, gotta go fix something there. So this was actually 97.68. That's going to be important. 98.2 plus 2 times 0.26. So I subtract 2 standard deviations. Now I'm going to add 2 standard deviations. And then we get 98.72. Well, that doesn't match what I have here. So let me look at my almost all, which we said is 99.7%. So in that range, that is where we go out 3 standard deviations. So now I'm going to take 98.2 and subtract 3 times 0.26. which is going to give me 97.42. And then if I take 98.2 and I add 3 standard deviations, that's going to give me 98.98. And that is the range that we see here. So if I have 60 people in my group, what I'm expecting is that this is representing that 99.7%. So as a decimal, that's 0.997. This is why we're going to say approximately all. I get 69.92. And we can't have partial people, so we round this up to 60. So really what I expect is that all people in that group should have a temperature in that range, as long as they're healthy people. Okay, so the last one, which is the thinking problem, decide in each case whether it would be appropriate to use the empirical rule. So remember, you need a bell-shaped curve for the empirical rule. So this one seems to approximate bell-shaped. I'd say that one was okay. That one is skewed, so I'd say no. This one's also skewed, so I'd say no. And this one's approximately bell-shaped, so I'd say yes. What's important here is that I can only use empirical rule on those bell-shaped curves. Now, we still like to figure out probabilities when we have these skewed curves, which is going to give us our next rule that we have here. So Chebyshev's inequality, it's going to be the rule that we can use pretty much for any kind of distribution, but it's really, really used for ones that are not bell-shaped. So when the distribution is bell-shaped, we use empirical rule to approximate proportions of data within 1 or 2 standard deviations of the mean, or sometimes 3. Another rule is called Chebyshev's theorem, or inequality, sorry, it's also called theorem, holds for any data set. So if we have skewed data sets, we can use Chebyshev. So in any data set, the proportion of the data that is within k standard deviations of the mean is at least 1 minus 1 over k squared. So what that's telling me is that if I have data that is 2 standard deviations from the mean, the proportion that I expect to find in that 2 standard deviations is going to be 1 minus 1 over 2 squared, or 1 minus 1/4, or 3/4, or we could say 75% to be in that range. If we do 3 standard deviations, in that case, we're going to have 1 minus 1 over 3 squared, which is 1 minus 1/9, which is going to be 8/9, or roughly 89% of the data should be within 3 standard deviations of the mean. So this is any kind of distribution. Like I said, this seems a lot different from when you were looking at a bell-shaped curve. Bell-shaped curves are a little more, your probabilities are probably a little more correct than you'd say in Chebyshev's, because Chebyshev is taking care of any kind of distribution. It doesn't have to be bell-shaped. Or the public health study, systolic blood pressure, trying to remember how to say that right, who was measured for a large group of people. The mean was 120 and the standard deviation was 10. What information does Chebyshev's inequality provide about this data? So what we can do is this. Chebyshev doesn't help us with 1 standard deviation. We can only do like 2, 3 standard deviations. It's not going to help us with 1 standard deviation, because what's going to tell you is that the incorrect data is pretty much what you can get from it. So we are going to compute the following. We are going to have X bar minus, sorry, what was I doing? The mean is, sorry, the mean is 120 and the standard deviation is 10. Okay, what information do we get? So we know that by Chebyshev's theorem, if we look at two standard deviations from the mean, that is going to represent 3/4 or 75% of my data. So the range for two standard deviations is x minus 2 standard deviations. So 120 minus 2 times 10, so we get 100. And then my mean, 120 plus 2 times 10, my standard deviation, which is 140. So 75% of people or blood pressures we're going to say readings because we have to say something. So 75% of systolic blood pressure readings are between 100 and 140. So your blood pressure has two parts. This is systolic, and I'm trying to remember the name for the other one, but there's a second part to it. So if we do look at three standard deviations, so we already established that three standard deviations is 8/9 or 89%, but we just need to figure out those ranges again. So we have our mean minus three standard deviations, which is 90, our mean plus three standard deviations, which is 150. So 98% of my systolic blood pressures are between 90 and 150. Okay, so like I said, it's given me an approximation here. May not be the best approximation, but this is basically for any kind of data set that I'm not sure is bell-shaped. So the population of US presidents has a mean of 55.5 and a standard deviation of 7.3. Using Chebyshev's inequality, we want to approximate how many, so this is one that you were supposed to be answering, but approximately how many of our presidents took office for the first time when they were between the ages of 33.6 and 77.4. Okay, so remember, we're using Chebyshev's inequality, so we cannot look at one standard deviation and get an approximation. But I can look at two standard deviations, and I could look at three standard deviations. I can keep on going to four or more if I wanted to. We'll just start here. So two standard deviations, we know this represents 75% of my data, and three standard deviations is going to be 89. So we just need to figure out those ranges. So first, for two standard deviations, 55.5, and we're going to subtract two standard deviations of 7.3. And if I do that, I get 33.6. So it looks like this is what we're going to need, the two standard deviations. Let's just double check. So if I instead add two standard deviations, well, that's 77.4. So yeah, so we don't need this. We just needed this right here. So if we're between the ages of 33.6 and 77.4, that is my range of two standard deviations. And then by Chebyshev's inequality, that two standard deviations is going to give me that 75%. So we're expecting that 75% of presidents should have an age that is between 55.3 and, or sorry, a range between 33.6 and 77.4. In actuality, like I said, this isn't always that true. This is 44 out of 45 presidents are in there. So in reality, it's actually 98% are in this range. Like Chebyshev's theorem is, it's useful. It gives us at least something. We can say at least 75% are in there. But it's not usually that close. This is actually closer to what empirical rules said, because empirical rules said that should be 95%. So Empirical is really good. Like I said, when you have bell-shaped curves, the approximations are way better. And this is just not quite bell-shaped, it's not that far off. But Chebyshev does give an approximation, at least 75%. It just may not, like be very close to what the real approximation is. Which brings us to the end of all this. So both Chebyshev's inequality and the empirical rule provide information about the proportion of a data set within a given number of standard deviations of the mean. So it gives us that percentage or that proportion. The advantage of Chebyshev's inequality is it applies to any data set, whereas empirical rule only applies to data sets that are approximately bell-shaped. So if we have non-bell-shaped curves, we at least have a way to assess probabilities or proportions. A disadvantage of Chebyshev's inequality is that for most data sets, it provides only a very, very rough approximation. So like we saw the presidents, the actuality is that within 2 standard deviations is actually 98% of all the presidents' ages. By Chebyshev, though, it said it's about 75. So it gives very, very rough approximations that can be really off the mark. But the plus side is if my data is really skewed one side or the other, I have some way to approximate probabilities or percentages.